I am going to propose and theoretically compare three resonant switched capacitor converters with a fixed voltage conversion ratio of 1.5 for electric vehicles onboard boost converters. Existing ordinary charging stations for electric vehicles cannot charge high-voltage batteries, such as 600 and 800-volt batteries, unless onboard boost converters bridge the voltage gap. In this talk, I am going to talk about resonant switched capacitor converters with a fixed voltage conversion ratio of 1.5 that can cover both 600 and 800-volt battery voltage ranges. Three converter topologies will be proposed and analyzed, followed by the experimental verification test using a 1 kW prototype. Finally, I will show the results of theoretical comparison from the viewpoint of power conversion efficiency and power density. This is the outline of today's presentation. First, I will talk about the background of onboard fixed conversion ratio converters and briefly review conventional boost converters. Next, I will show the three resonant switched capacitor converters with a fixed conversion ratio of 1.5. And lastly, these three topologies will be theoretically compared from the viewpoint of efficiencies, losses, component volume, and power densities. But before the theoretical comparison, the theoretical model will be experimentally verified by the 1 kW prototype. Ordinary existing charging stations are designed to charge 400-volt batteries, and its maximum output voltage is typically 500 volt. Meanwhile, we are seeing that a lot of automotive companies are developing high-voltage batteries such as 600 and 800 volt in order to improve the fast charging performance and to extend cruising distance. But the existing 500-volt charging stations cannot charge such high-voltage batteries unless the voltage gap is bridged by boost converters. Electric vehicles employing an 800-volt battery have already been commercialized, and onboard boost converters with a fixed conversion ratio of 2 is used. However, with such converters, the existing charging stations cannot cover the voltage range of 600-volt batteries. If the fixed conversion ratio is 1.5, not 2, the existing charging stations can cover both the 800 and 600-volt battery voltage ranges. Traditional 2-level or 3-level PWM boost converters are the most straightforward approach. However, these converters are not suitable for fixed conversion ratio applications because of relatively large inductors. Another major drawback is hard switching operations that would be a stumbling block to shrink the converter volume by pushing up the switching frequency. On the other hand, resonant switched capacitor converters are the best suitable topology for fixed conversion ratio applications. In the resonant radar RSCC, the current waveform is sinusoidal, and all switches and diodes operate with zero current switching manner. What's more, the inductor volume reduction is also feasible thanks to the resonant operation. The 3-level flying capacitor converter can operate as a resonant converter by tuning the inductance and capacitance of flying capacitors. The inductor current is a rectified sinusoidal wave that contains a DC current component, so the inductor can mitigate negative influence of skin effect and proximity effect that increase the resistive component at high frequencies. This converter also achieves ZCS operation. These resonant SCCs might be an attractive solution, but the big problem is that voltage conversion ratio of these converters are just 2, not 1.5. In other words, these resonant SCCs cannot be used unless the conversion ratio is modified to be 1.5 somehow. There are the three resonant SCCs that achieve a fixed conversion ratio of 1.5. All topologies contain one resonant inductor and two flying capacitors or resonant capacitors. These converters are a unidirectional converter, but they can be modified to be a bidirectional converter by replacing diodes with switches. These converters operate with ZCS manner, and their inductors can be small thanks to the resonant operation. From next slides, let's take a look at fundamental operation principles of respective topologies. The first one is the resonant flying switched capacitor converter, or RSCC, that can be derived from conventional 3-level flying capacitor converter. The flying capacitor in the conventional converter is replaced with what we call flying switched capacitor cell. The series and parallel connection of capacitors in this cell are automatically switched depending on the current flow directions. This converter is very simple and its operation principle is also simple. What's more, voltages of flank capacitors can be automatically balanced and therefore voltage balancing control is no longer necessary. This converter operates with two modes. Right-hand figure shows theoretical key waveforms. From top to bottom, the gating signals, current of flank capacitors, and current of the resonant inductor. In mode 1, the low side switch is on and flank capacitors in the cell are charged in series, and therefore their average voltage is half the input voltage. And the series connected flank capacitor resonate with the inductor. In mode 2, the high side switch is turned on and flank capacitor in the cell discharge in parallel. The input voltage source is connected in series with flank capacitors, so the output voltage is 1.5 times greater than the input voltage. Since two flank capacitors are parallel connected, the combined capacitance in mode 2 is 4 times that in mode 1, so the resonant frequency in mode 1 is twice that in mode 2. And please be noted that the current amplitudes in mode 1 and mode 2 are the same, and the average resonant frequency is equal to the switching frequency. The second topology is the 4-level resonant flank capacitor converter, or 4-level RSCC. The topology itself is identical to a traditional 4-level flank capacitor converter, but the inductor and the flank capacitors are designed to resonate. Similar to the traditional 4-level converter, average voltages of flank capacitors are 1/3 and 2/3 of the output voltage. The average resonant frequency is 1.5 times that of the switching frequency. It's a bit higher than the previous topology, so it can reduce the volume of the resonant tank. However, voltage balancing for flank capacitors is necessary, similar to traditional flank capacitor converters. Besides, peak current in some operation mode is prone to be large, and it would increase RMS current as well as joule losses. This topology operates with 3 modes. In mode 1, the bottom switch is on and right-hand flank capacitor resonates with the inductor. In mode 2, the second bottom switch is turned on. As you can see, two flank capacitors are connected in series, and therefore the resonant frequency in mode 2 is higher than that in mode 1. In mode 3, the upper switch is on and the left-hand flank capacitor resonates with the inductor. In summary, only one flank capacitor takes part in the resonance in mode 1 and mode 3. In mode 2, on the other hand, two capacitors are series connected, which increases the resonant frequency in mode 2, as can be seen in the right-hand figure. More importantly, the current amplitude in mode 2 is rather higher than that in other modes. A single switching cycle contains 3 half-sinusoidal waves, so the average resonant frequency is 1.5 times that of the switching frequency. The last one is the 3-level resonant switched capacitor converter, or 3-level RSCC, which is the extended version of the conventional resonant radar SCC. A 3-level flank capacitor circuit is incorporated in order to achieve the 1.5 voltage conversion ratio. The flank capacitor is designed not to resonate with the inductor to avoid a multi-resonant operation. Thanks to the 3-level flank capacitor circuit, the resonant frequency can be twice the switching frequency, and the higher resonant frequency translates into small resonant tank. However, voltage balancing for flank capacitors is necessary. What's more, since the resonant inductor is connected in series with the resonant capacitor, the inductor current is pure sinusoidal wave that increases the inductor's resistive component due to the skin effect and proximity effect. This converter operates with 3 modes. In mode 1, the resonant tank is charged in series with the flank capacitor. In mode 2, the resonant tank is discharged to the output port. In mode 3, the resonant tank is charged by the flank capacitor. In summary, this converter has only one resonant frequency, and the current amplitude of the resonant tank does not change. A single switching cycle contains 2 resonant periods, so higher resonant frequency would reduce the volume of the resonant tank. Let me briefly compare the 3 resonant converters. Inductor currents of these two converters are rectified sinusoidal waves that can mitigate the negative influence of skin effect and proximity effect because these current waveforms contain DC component. From the frequency viewpoint, 3-level RSCC would be the best. As for the RSCC, the remarkable benefit is that this converter does not need voltage balancing control or circuit for flying capacitors. Each topology has unique benefits and drawbacks. So, from the next slides, we are going to quantitatively compare using theoretical models. Passive component volume can be determined by the maximum energy stored in a component. The maximum energy of a capacitor is expressed using a capacitance, peak voltage, and derating factor. The capacitance is a function of a ripple factor that is determined to be 0.2 for resonant capacitors and 0.05 for input or output smoothing capacitors. The maximum energy of an inductor is also expressed using an inductance, peak current, and derating factor. The right-hand figure shows the energy densities of passive components. Energy densities of capacitors are 10 times to even 1000 times greater than those of inductors. For onboard battery chargers, film capacitors are appropriate, and their energy densities are around 10 microjoule cubic millimeters. Energy density of inductors, on the other hand, are around 0.3. From these energy densities values and maximum energy equations, we have calculated theoretical passive component volume. The heat-sink volume is estimated based on the Cooling System Performance Index, or CSPI, which is the inverse of thermal resistance per volume. The CSPI values are typically 1 to 4 for natural air cooling and 5 to 10 for forced air cooling. The heat-sink volume can be estimated from the CSPI and heat-sink ambient thermal resistance that is a function of the total loss of semiconductor devices. Experiment. We built a 1 kW prototype of the resonant flying switch-to-capacitor converter. The input voltage was 400 volt and the switching frequency was 65 kHz. The bottom right-hand figure compares the component volume of the prototype and the theoretical values. The inductor in the prototype was rather smaller than the estimated one because the energy density of the selected inductor was relatively high. Overall, the prototype and calculated volume agreed very well. This slide shows the measured waveforms and power conversion efficiency. The measured output voltage was 600 volt. However, the measured inductor current was not pure rectified sinusoidal wave. At the moment of turn on and off, the inductor current sharply changed due to the existence of parasitic capacitance of MOSFETs and diodes. The inductor resonated with all parasitic capacitances combined, and this parasitic resonant frequency was much higher than the resonance of the flying capacitor. To avoid such parasitic resonance, semiconductor devices with low parasitic capacitance should be selected. Although the inductor waveform was a bit different from the theoretical one, the measured efficiency matched very well with the theoretical efficiency, verifying the theoretical efficiency model. The full load efficiency was as high as 99.2%. Theoretical comparison. The left-hand figure shows the theoretical efficiencies of 3 topologies. The full load efficiency were comparable and were around 99%. In the right load regions, on the other hand, characteristics were very different. This is because in the RSCC, the fixed loss took the significant portion of the total loss. The right-hand figure shows the estimated loss breakdowns at 50 kHz and 200 kHz. The fixed loss here is the parasitic capacitance loss that is dependent on switching frequency and off-state voltage. The off-state voltages of other topologies are half the input voltage. However, the off-state voltage of the RSCC is equal to the input voltage. So the largest fixed loss in the RSCC is due to high voltage stresses. Let's see component volume. The left-hand figure is the component volume breakdown at 50 kHz and 200 kHz when the CSPI is 2. In all converters at both frequencies, the heat sink volume is a predominant factor. Passive components shrink as the switching frequency increases to 200 kHz. But heat sink volume increases because frequency-dependent parasitic capacitance losses increase. This result suggests that the 3-level RSCC can minimize the passive component volume thanks to the highest resonant frequency. Because, as can be seen in right-hand figure, the resonant frequency of the 3-level RSCC is highest and is twice the switching frequency. According to the theoretical loss model and component volumes, we have derived parallel front curves of efficiency as a function of power density. The x-axis is power density and y-axis is efficiency. When the CSPI is 2, which corresponds to natural air cooling situation, all topologies show very similar characteristics, and the optimum switching frequency from the viewpoint of power density would be around 100 to 200 kHz. When the CSPI value increases to 10, the forced air cooling situation, the 3-level RSCC and 4-level RFCC would achieve higher power density. However, as I mentioned earlier, these topologies require a flying capacitor voltage control or circuit. Overall, the optimum switching frequency to maximize power density would be a few to several hundred kHz. At high frequencies, parasitic capacitance losses become predominant and increase heat sink volume, eventually reducing power density. So, in order to push up the switching frequency to further increase power density, a ZVS operation is indispensable to eliminate the frequency-dependent parasitic capacitance losses. Conclusions: I have proposed 3 resonant switched capacitor converters with a fixed voltage conversion ratio of 1.5 that bridge the voltage gap between the existing charging stations and onboard high-voltage batteries. Each converter has their unique benefits and drawbacks. The RFSCC is the simplest converter. 3-level RSCC and 4-level RFCC would achieve higher power density, but the drawback is the necessity of flying capacitor voltage balancing control. Finally, theoretical analysis suggests that a ZVS operation is indispensable to achieve higher switching frequency operations and to further increase power densities. Thank you for listening to my presentation.